Hi, welcome to the ZTF Summer School. My name is Shri Kulkarni. Hi. Okay, welcome to the ZTF Summer School. My name is Shri Kulkarni, and I'm the principal investigator of the Zwicky Transient facility, otherwise called as ZTF. This is how it all began. I mean, the universe. After the Big Bang, the universe is incredibly homogeneous. The density of matter and energy at this point of the universe and in this point of the universe, some far away, was almost the same to 1 part in 10 to the 5, not 0. So those small inhomogeneities, thanks to the long range of gravity, grew, and the dense parts of the universe became denser at the cost of the less dense parts of the universe. And dark matter and matter coalesced into stars, galaxies, and clusters, which is what we are now seeing at this low redshift here, Z of nearly 0, which is the present time. The universe is highly structured in contrast to what it began. The universe is also rather simple. Good time to be in a chemistry student because there's only hydrogen and helium, and with a trace amount of lithium and deuterium and so on. And but how did the periodic table get built up? This is a great quest that began in the last century. Both how stars act as fusion reactors and supernovae complete the reaction phase, and how the periodic table gets built up. And in a nutshell, this is the grand motivation that began the Zwicky Transient facility, or more accurately, its predecessor, the Palomar Transient factory, PTF. So now we know that when stars die or end their life, they undergo through a series of fusion reactions. They produce elements increasingly up into the periodic table. The father of what we now call as modern time domain astronomy is Fritz Zwicky, who was a professor of physics that was hired at Caltech when Caltech began the 200-inch project in the late 20s. While awaiting the completion of the 200-inch project, Zwicky was busy with a whole bunch of ideas, including a systematic time domain survey of the universe with an innovative, for that time, wide field telescope with which he photographed the sky repeatedly and found supernovae. In fact, for a very long time, Zwicky had the record of the number of supernovae found by one person. If you want to see this pioneering telescope, the Palomar wide field 18-inch telescope, you can go to the Palomar Observatory Museum, and it's been restored. It's a beautiful equipment. We jump forward from the 20s, 30s to the modern times, and the quest to understand the periodic table is still continuing. We all know a frontier area is gravitational wave astronomy, and one of the singular discoveries from the LIGO and Virgo collaboration was the discovery of coalescence of 2 neutron stars, which after they coalesce, they presumably form a black hole, but more importantly, a small amount of debris is ejected, which forms even higher Z elements, that is, elements way up into the periodic table with higher atomic number. So the things that we fancy, gold, platinum, silver, they all come from stars which have been dead once and die again just to make the small amount of precious metals. The general spirit of PTF and ZTF is summarized on this slide. Here's a statement by Zwicky, which I'll read. I soon became convinced that all the theorizing would be empty brain exercise and therefore a waste of time unless one first ascertain what the population of the universe really consists of. By which Zwicky was meaning the following. The universe is got more imagination than we have. Think of this way, our galaxy has 10 to the 11 stars. There are approximately 10 to the 11 galaxies in the universe. That means there are 10 to the 22 stars in the universe. So in a sense, what Zwicky was saying is that there's so many possibilities, single stars, binary stars, triples, quadruples, and interactions thereof, and subsequent interaction like neutron star, that you could get all sorts of really strange outcomes. And we know this is true now. Okay, if you accept this idea, then in order to make a discovery, you really need to find signals, and discovery is therefore pure function of technology. And as it now turns out, algorithms. You can have a lot of data. If you don't have algorithms, you're just sitting with a lot of data. If you have lots of data and algorithms and still need people, it'll be very slow, it'll be slowed down. So I contribute an original statement to this slide. The best way to do astronomy is to get the astronomers out of the dome. For some reason, this seems to annoy other astronomers. Anyway, so a corollary of that is automation leads to efficient discovery. Okay, so the concept of PTF was a factory to systematically study cosmic explosions. And the basic idea, as in a factory, is we have an assembly line, and here's the first part of the assembly line is the 48-inch Ocean telescope, which is also a wide field telescope, the successor to the 18-inch Palomar telescope. And its main job is really to simply image the sky incessantly. Every 30 seconds, get a new picture, analyze the data in real time, and send candidates for confirmation at the 60-inch telescope, which has a multi-band imaging photometer. Sometimes getting additional information like multi-band helps you decipher whether this is an ordinary nova, supernova, and if so, what kind? Is it an M-dwarf flare, and so on. But the final arbiter is, in fact, the 200-inch telescope, which actually has a spectrograph. And a spectrum is a pretty unique signature of the elements that the star or the event has. Okay, so this factory works night in, night out with the 48-inch and the 60-inch dedicated to this cause. And we pull in the 200-inch a fair bit of time, but not all the time. I wish we could. Okay, so here's a phase-space diagram, and I call it in the honor of Zwicky, the Zwicky diagram. It shows the peak luminosity on the y-axis in magnitudes in the V-band, and the duration in x-axis, 1 day, 10 days, a year. And roughly the lay of the land, you know, if you go back to about 20 years, is thermonuclear supernovae, otherwise known 1A supernovae, very famous for their role in cosmography. They also are the biggest producer of iron in the universe, by the way. Classical novae, which are basically explosions on the surface of white dwarfs. They're not catastrophic like supernovae. And then core collapse supernovae, these are massive stars that end up making black holes or neutron stars. Okay. And thanks to the work of a number of time domain facilities that basically came about after the millennium, Pan-STARRS 1, Palomar Transient Factory, later Assassin, Atlas now, this landscape turns to be very, very rich. So you can see that we have apparently a class of supernovae which only make calcium, and another class which are luminous and red at peak. And in fact, these are probably two subclasses here. Some class for a while they were called as 0.1A supernovae. We don't know what they are. And then super luminous supernovae. Okay, so PTF began in 2009, and here we're in 2021, and I need to condense all this into a short time. So let me just go directly to the methodology and technological developments that made all this discovery possible. Remember, my thesis is build the gizmo, discoveries will happen because we have a rich universe to discover, to explore. In phase one, which is the classical Palomar Transient factory, ran for 4 years, we were the first to implement machine learning in a massive way to determine candidates. Okay, after image subtraction, there's a lot of junk you create, and a human can say that's a good subtraction. But we use machine learning led by Josh Bloom, who's now professor at Berkeley, and he'll come back again at the end of this talk. We also understood how to decrease the latency that is between getting the imaging data and characterizing the event. And we are able to, towards the end of PTF, actually find a supernova. Within the same night, we were able to follow up spectroscopy, and it led to a bunch of Nature papers, which is a big thing in our field. The success of PTF led me to IPTF, the Intermediate Transient Factory. And here we introduced mixed cadence, multiband observing, and robotic integral field unit spectroscopy. This is basically robotic spectroscopy, which will turn out to play a very big role as we go into the ZTF era. We also, as a part of Leo Singer's thesis project, demonstrated how to search needle in a LIGO haystack, which is how to find electromagnetic counterparts, in this case for gravitation, for gamma ray bursts, but in large fields. The success of IPTF was such that we, in fact, proposed to the National Science Foundation for the Zwicky Transient facility, and which ran from 2018 to 2020. And it succeeded so well, we actually now into phase 4, which is Zwicky Transient Facility Part 2. Okay, the motivation, and I guess it was a compelling motivation to NSF because they funded us, was ZTF would serve as a precursor or a stepping stone to the national flagship, LSST, which has now been renamed as the Vera Rubin Observatory for Time Domain Astronomy. We started the era of industrialization of alert distribution, and Matthew Graham, who's a project scientist, and will follow my talk, he's going to tell you a bit of that. Okay, so ZTF is now a very large project. In addition to Matthew Graham that I mentioned, we have Eric Belm, who's a survey scientist. He's a professor at University of Washington, Seattle. And we have some very dedicated and very clever engineers and scientists who built the system and who maintain that. Richard DeCaney, who's a project engineer. He's at Caltech. Reed Riddle is in charge of robotic operations. Remember, these two telescopes are completely robotic. We don't operate them by people. Roger Smith was the lead for the camera system. Don Neal is the lead for the SCDM system. Okay, so the signature strategy or the signature strength of ZTF is its wide field. We have 47 square degrees. Here's LSST, almost 10 square degrees, but it's behind a 6-meter telescope effectively. Pan-STARRS 1, 7 square degrees, it's behind a 1.8-meter telescope. Supreme Cam, Hyper Supreme Cam Subaru telescope behind an 8-meter telescope. So we are the largest field of view on the smallest telescope in this collage, which means we do wide exploration of the sky, looking for the brightest things. Of course, the trick is to be faint enough that you get enough sources, but bright enough that you can follow. So we are brighter than a couple of other surveys, which do find brighter objects, but only a few in a year, relatively speaking. Okay, our capacity to find supernovae, for example, is about 10,000, of which we only classify about 2,000. So that should start giving an idea of the importance of follow-up or the bottleneck for follow-up. Okay, in ZTF phase 1, here are the technical achievements, some science achievements. We had the first artificial intelligence discovery of comets, now several in the back. We have routinely discovered Atira asteroids, or asteroids which are within or crossing the Earth's orbit. And the first discovery of Vatira asteroid, which is within the crossing Venus. And in fact, just last week, we found a second one. Postdoctoral fellow Ilaria Cayazzo, she found the most massive white dwarf to date. Its size is similar to the size of the moon. As you know, white dwarfs, the more massive they are, the smaller they are. Where ZTF is a major source of superluminous supernovae. It's now very routine. It used to be a big deal when we started in PTF. Nature papers here and there, but now it's like, oh yeah, another supernovae. Routine studies of supernovae within hours of shock breakout, what used to be heroic efforts of finding things that just exploded, we more or less can schedule it. So, I'm not very interested. Let's do this experiment next week and then schedule the our follow-up, because we know we are guaranteed of finding a young supernovae. Discovery of afterglows from gamma ray bursts without even being told it's a gamma ray burst. Okay, I would consider that's a technical coup. And we may have even found a new type of relativistic transients. This is to be confirmed. Okay, so I spoke a bit about how we are in the era of the gravitational wave astronomy. So gravitational astronomy has its own bands. So for example, in radio astronomy, the radio astronomers talk of low frequency radio astronomy, which is like, a gigahertz, 100 megahertz. And then high frequency astronomy, like in ALMA, like a millimeter astronomy. In the same way, gravitational wave astronomy also has bands. LIGO, the ground-based system, is sensitive to gravitational waves with frequency, or let's say between 10 hertz and maybe a kilohertz. That's its sweet spot. Okay. In contrast, a European mission called LISA, its sweet spot is about 10 millihertz to a tenth of a millihertz. Okay, so that's over here. So LIGO is very good at finding two neutron stars coalescing. LISA is very good at finding two white dwarfs coalescing. Remember, the system is larger. And in a great thesis topic by a graduate student, Kevin Burge, he more or less doubled or tripled the kinds of binaries that LISA will be able to easily detect once it's launched roughly in the mid-30s. Okay, and these binaries that Kevin's finding, they're very special because they're eclipsing. So you know their geometry, so you can really use them to calibrate the LISA mission. Okay, so now we are in ZTF phase 2, which we began last fall, and will last for 3 years. That means through September 30, 2023. Large number of institutions around the world, just as in PTF, ZTF, but it's grown now. We go all the way from Taiwan back to the US, through Asia and Europe. And what are the main goals of this project? Well, we will continue our solar system work. We'll continue to press on the high redshift of the universe with this relativistic transients. Even though transients was not a big thing when PTF began, with the accumulated data as well as the improvements in technology that allows us to do very good photometry, stellar astronomy has become a major part of ZTF. And this aspect of the project is led by Professor Tom Prince and his students and postdoctoral fellows. And I already spoke glowingly of the search for this highly compact double white dwarf systems, the orbital periods of only minutes. Okay, that's very much a game in progress. With large data, you need more algorithms, more cleverness. So we're implementing for machine learning, for classification and AI discoveries, massive computing. So things that are happening in the industry, thanks to some very bright young people, Ashish Mabel and Dima Duev, we are really bringing in latest industry progress in, for example, in TPUs for time domain astronomy. Discovering supernovae as they're being born is, I would say, will keep us very productive and busy for another few years. And then we are cooperating with a major Russian-German mission called SRG to study helpless stars as they're being shredded by nuclear black holes, also called as tidal disruption events. I'll end this talk by talking of just one program, which is the largest systematic program to address fundamental questions across modern astronomy this is the largest systematic supernova program. Okay, this is the Bright Transit Survey, not very imaginatively named. It's headed by two young people. Daniel Perley is a professor at University of Liverpool and John Moores, Liverpool University in UK. Christopher Fremling is a senior postdoctoral fellow at Caltech, and a number of people around the world. This is a major effort. And you can see this in galactic coordinates, in equatorial coordinates, how well we are peppering the sky with discoveries of supernovae. Okay, what used to be, before PTF began, the biggest systematic search, narrated about 100 supernovae in a year. That is one every 3 nights. We can now do a few a night. In fact, maybe our record is 10, I'm not sure. But our capacity to find supernovae far exceeds our capacity to classify them. And this is my pet peeve that many astronomers say, my widget will discover gazillions of supernovae. I say, no. It may identify supernovae candidates, but in order to complete the story, you have to know where it is. And you can do that if you have exquisite light curves or good spectroscopy. Otherwise, you just have candidates. Okay, so what's shown here is that data is rolling by. Blue is core collapse, red is 1A, thermonuclear, and black are dwarf novae, which are some variation of cataclysmic variables. Well, as I said, just identifying candidates, I think, is not where the current frontier is. You must have an end-to-end plan, and we are very happy that we thought through this some years ago. So we have a dedicated classification engine, a spectral classification engine, mounted on the P60, the 16-inch telescope, and it's a spectrograph that is fine-tuned for classification. It's called a spectral energy distribution machine. And thanks to this 10 things work in tandem, we're able to do about 100 classifications per night. And here I have to acknowledge help from our colleagues at UC Berkeley, Alex Vendupenko, and others who bring in Lick Observatory to add over 20 or so supernovae per month also. Okay, so this is a very large number of supernovae. This should be the foundational data for all kinds of fundamental issues in the deaths of stars. Well, look at the quality of this data. These are there's a collage of light curves. It's very good photometry for a ground-based system, which has got such a large field of view. It's a tribute to the hard engineering that's been done by the COO team. Here's back to the Zwicky diagram. Well, you can see it's getting slowly populated. I'd be surprised if 10 years from now you come and it's all over the whole place, the whole phase space diagram is filled. So let me end by saying I talked a lot about astronomy, a lot of technology, and the fruitful interaction of astronomy and technology. But I also want to tell you that astronomy can make you rich also. Not guaranteed, but can sometimes make you rich. So remember I said how we pressed on machine learning, and then young Josh Bloom led it. Well, after he became faculty member at Berkeley, he took the machine learning experience at acquired PTF, and with some other colleagues also, I founded a startup called Wise.io. And a few years later, they sold it to GE. Mind you, when GE stock price was still high up. Okay, so that goes to show you, while we use technology, sometimes we can go back and make technology happen. In 2016, I gave a talk at MIT, and a young person in the audience said it inspired him to start another startup. And my talk was on how automation is the key to high productivity. So here's Rohan Murthy, and he founded a company called Sirocco.com, which is all about automation and artificial intelligence, but in software. Okay, so let me end here and say that Matthew Graham, the project scientist, will now give you the technical details, in some sense, the nuts and bolts of ZTF. Welcome again to the ZTF Summer School.